problems. What do I cook? Pasta, I make tofu.
I had to go over a few slides and then jump back to the
Stop just to introduce something in between. You're running the show.
Yeah. I wish I was I just am bad at like planning ahead and getting stuff for
How'd you cut yourself on?
Just cutting an onion.
That like adds flavor to it.
Yeah, my day has been pretty much all downhill from there.
There's someone who was cutting, I think, a tomato or something, garlic, and sliced it with finger, and then
I haven't slept last night, so
no, I'm gonna keep
that's why I'm a little confused today.
then like weird.
You want coffee?
No.
Like crippled.
I had 2 meetings today, one with Misha, one with another professor working with Misha, so kind of too busy.
One second. Just we have a subset of people I know. There are enough many people that are still alive in the course, submission-wise. Thinking about midterm. Next week you are in vacation, right? And if you do it right after midterm, it can be on Tuesday, but then we don't have a review. And I tend to think the 27th for the midterm. And the material will be like not what I covered in the last week.
Wait, Thursday the 27th?
I think that Thursday and then Tuesday I can have reviews.
You mean Wednesday? Wednesday.
Of course,
The
it's
26th.
Yeah.
You got Tuesday.
ADHD, you're absolutely right. So this week is taken. We can have this date 17 or 19 when you're just back. I'm not very happy about it because if you need help with homework, it will push, but it's doable. Wednesday has slight preference over Wednesday because they have the Monday. Wednesday is better than Monday because we have time to do a review on Monday. If it's Monday, then we can have the review over the weekend, which is also doable. So it's just a week preference, but what makes sense to me is to have the 26 if you don't have big conflict against. But it's not something that I care about. If you want another date, it's entirely up to you. Or entirely up to other conflict, yeah.
Did a lot of people drop?
No, we are, the website 26. And homework 2 was close to it in the submission. But a lot of people realize that there are other ways to study graphics that doesn't involve coming to class. It's not convenient time. And I'm not really not encouraging anybody, but at least I don't know about people. I know about 3-4, so it shouldn't be. Anyway, I think that somewhere between 18 and 22 will be perfect time. Yeah, 18 to 22, that's a good size for this course. Okay, so temporarily 26 is midterm. Convince with everybody. If you have some emergencies, then talk to other people. Okay, Amir, all yours. What? Not a good day?
Oh no, I was just like, wow, it's a teenager.
Plans for
what we need to focus for this course is the vertex shader and fragment shader. Vertex shader processes the vertices. You actually the actual pixels. So vertex shader processes the triangles. You enter the data through attributes, and through varying, it does interpolation to the fragment shader. And your final, this GL frag color here is your final color for each pixel.
I'll start even one step higher. On your CPU, there are things that look at all your data, in particular the vertices of all your triangles, your viewpoints, and it computes the geometry and the modeling part, generates these matrices of all the L that we project everything correctly. That's what all the geometric primitives that runs on the GPU. This part also compile and prepare all the various programs that Amir mentioned, where they create the vertex shaders. That is, these are programs that are in the code, needs to go to compilation so that you're happy to run them, and the program on the CPU will send them to your GPUs for but once per vertex. So what determines the complexity right now. One operation, even not for triangle, it's one operation per vertex, and a little program that works on this what happens to each individual vertex. And this program in terms, again, who decides what to wants where all sits in the GPU, but once you know for a triangle what are all the attributes for its vertices, V1, V2, V3, the fragment programming or the pixel programming will do the rasterization. Namely, it will do, now it all puts together with the algorithm that we mentioned to compute barycentric coordinates, the alpha, how much weight each vertex is. Now my fragments program will start computing it per each row of each triangle. Compute these vertices. We said about how the weights of every pixel is computed. The only loop that you need to write is push every vertex, or actually here is an array of vertices. You go and read each vertex, and now at the bottom line there comes the rasterization that, based on the resolution that you specified, it will compute the barycentric coordinates for each and every pixel that is relevant. Well, from the barycentric coordinates, it will interpolate the various properties. In addition, various properties were included the z-value. So since I know the z-value over three triangles, I can know the z-value of each point in the triangle, at least each pixelized point. And it is sent to the GPU, to the depth buffer, to ask who are any of these pixels seen by the user. Worth mentioning in all this part, you want to do, you have in your mirror program, a rotation of an object. The vertices of the objects that you are rotating are not going anywhere. Your last hope, you'll try to avoid as much as you could, moving the location of any particular object. Make sense? Each object stays where it is unless it's multi-piece object, multi-robots, parts, and then sure, there are more involving of coordinates that maybe you have to do. In general, in the examples that we'll play with, objects, the geometry stays the same. What matters if you're rotating around the object is a matrix that is created here that takes into account where the user is and at which angle the user watches the world, will be sent all the way here, and it will be used to teleport each vertex from where it is in the model world, in the XYZ, in the input, into where the camera wants to see it. Yeah?
How is geometry stored on the GPU?
The geometry was included everything, in particular where the users watching everything, and prepare all the buffers that will be there, and fill one of them in vertices of triangles. Examples that Amir will show. Roughly, we'll prove where the vertices of every triangle, and we'll show what are these. Which vertex, or for each triangle, who are the vertices that define this triangle, and later on you'll say, I could have multiple programs that each one are called a vertex shader. I'll send each vertex at a time to the vertex shader. And now I have the triangles. I'll write a different program, but my CPU decides when to apply it. That says, oh, this triangle these triangles that you see right here, at some point you said that the texture of this triangle is a billboard with this person standing here. So the question of taking colors from the image, from the texture, and copying them into these triangles is not something that the user needs to worry about. It all happens miraculously underneath the hood. The moment that we told which vertex corresponds to which vertex in the image. The same goes with interpolation of shading. The same goes with interpolation of normals. Yeah.
Okay, so yeah, we wanted to.
No. I just wanted to set a bit structure, but examples.
Okay, so I go over this slide. I covered it yesterday. So we have attributes, uniforms, and varying. Yeah, so this is have inside your shader program. Then we need to send the attribute information, just like how I mentioned. Is that 2D, is that 3D, is that float, is that integer? We will see in the code. Then we need to send the uniforms, and the last command that you need to do that does all the magic and renders like a single frame is draw arrays. And it does updating the canvas, and you just repeat this rendering loop. Okay, before going to potential issues, let's get back to code and see how it works. So if you remember, that was example 0. So here there's no even depth buffer. Let's go to the source code. It's this one. I forgot to get my mouse. Okay, so
Should I bring your mouse?
nah, I can stay.
To bring it from my office?
Should be here.
I'll bring it.
It's a mouse. Right? Okay. So I go with the touchpad for now. I covered these parts last session. We start again the canvas. We start with WebGL. We check if the device has the capability. This is the code that we will go over for multiple examples. And then here we compile our program, the shader program. If you have any issues in your code, there will be an error here. Then we get the locations, attribute, uniform, and so on. So here I create the buffer for the attributes. And okay, there are a lot of commands here that these are like some fixed commands that you need to use. You need to bind buffer, the buffer that you created, to the GPU. And then inside this set geometry, we send the actual data that sends the actual data. So at the end of this function, these are some fixed positions for the 3D object. This is the function that sends the actual data from CPU to the GPU. Now let's get back. Yeah. So we do the same for texture coordinates. We don't have normals here. Now here I create a texture buffer to send the image to the GPU. Again, a lot of fixed commands and so on. This was, if you remember, it was kind of register-like for the GPU. A GPU has at least 32 images that can be activated at once. If you have more than 32, you need to unload some of them and load other ones. Again, I covered this stuff. Blend for alpha channel, depth test, and call face. So up to here, that is technically last session. Any questions? Good, good. So let's enter the rendering loop. So thank you. So so here, first we start with clearing the canvas. Yeah, so okay, these two commands are just for handling if we resize the canvas so that it doesn't stretch or something. It detects that you resize the canvas. This is for the clearing the canvas. You see that we have depth buffer and color buffer. Again, you don't need to pay attention to this stuff because mostly they will be given to you. Now, if you want to just see the depth buffer, you need to change these commands a little bit. But I will put most of them in the template because for homework 3, you need to show the depth buffer. Now, this command you use for homework 1 and 2, you can put an argument that just says kind of the time. You can get the delta and get some sort of frame per second. So here I just calculate the difference of the time and so on. I calculate some radian for like rotation angles and stuff. Okay, here I say to activate program. The program that we compiled before, I stored as global variable. I say activate it because we need to access these variables. Now, here I calculate the projection matrix and camera position and all this stuff. Mostly it will be given to you, but you need to do animation a little bit, just like homework 2, linear interpolation. So this is the utility function that I will give you, like not a function, like a file that calculates projection matrix for you. Yeah, so you need to multiply, like you can have a model matrix if you want to rotate your model. You can have projection matrix for sure if you want to rotate your camera. You need to multiply them, right, to kind of merge them. Remember that all your models are technically at 0, 0, 0. So any video game you see inside a rendering loop, what it does is that it translates the objects from 0, 0, 0, rotate all the stuff, and then multiply it by the projection matrix. So this is technically what I do here. Yeah, this is like the rotation matrix for the actual letter, the 3D letter and so on. Mostly I will just give you some functions to do that. Now let's go to the uniform. So here I'm sending the 4x4 matrix to the GPU. That's the command to send the 4x4 matrix. So this is the location. This is the actual matrix. I can't remember what this argument was, but you don't need to really care about it. This is the object matrix, and this is the memory location. So you see that here I send the texture location. I say that use kind of image 0, register 0, whatever. And this command is from OpenGL, uniform 1i. It means send one integer to this location, right? This is the location, the global variable.
Maybe I'll highlight what this matrix, after we multiply all things, we talked about projection matrix, normal projection matrix. It takes the 3D world and the camera parameters and just project it all on the image plane, putting all of them with the same Z. But there are a few other matrices, and just to hand wave a bit, we'll go furthermore with details, but just to hand wave about these matrices, we had all these triangles over here. Here is my camera. That's the direction that my camera is looking at. It's not the X, nor Y, nor Z triangle. But, and here is my hand used as one of these triangles that is definitely within the camera. So the GPU wants my hand to be at the X, to be just close to the Z axis, so the camera can see, because the camera is looking towards the Z axis that the GPU, the hardware expect to be. My hand is, but Z is over there, it's far, far away. What this matrix is doing is that before anything of this happens, the vertices bounding the triangle, which is my hand, these three vertices are multiplied by the world matrix that takes my hand and place it now nicely on the Z-axis where the GPU, the image plane, expect to see my hand is. Why? Because we computed it so the camera, the way the camera in our input where we had the eye and the look at, etc. Look at was looking at this direction directly into the hand. GPU expects my hand to be directed with the Z-axis. Every time that camera, that anything of it needs to look at the vertex, it first multiplies its coordinates in homogeneous coordinates, of course, 4 numbers, by the word matrix, which will put the hand in the right place. That's why you don't need to change the actual location of any of the geometric objects. You're rotating around it, like we had the F that you were never floating. The viewer was rotating around the F actually, and the location of the vertices of the F was staying in the same place. So in this aspect, I'd like to think about these matrices are, it teleport my arm to the place that the Z buffer wants my arm to be.
Yes, so now the next part is to tell the GPU what is the format of the data that we sent to the attributes. So this is again the buffer. So these are some fixed commands. We need to enable like vertex attribute, so on. This is the position location of the geometry. Here I say that it's 3D, it's float, normalized, no stride offset, no offset, and so on. So let's say you want to trim parts of your 3D model on the fly. Instead of sending a new buffer, you can just put an offset inside your buffer. But again, you don't need to really care about it much. So here now the GPU knows what is you can even have a 2D scene. You don't need to have 3D. You can even have like completely 2D world and everything works in 2D. So by now the GPU had the data, but now it knows how to process it. Remember, we are inside the rendering loop. So this is texture coordinate, another attribute. We say that it's 2D. Everything else is almost the same except the name of the variables. Now, this is the final command that actually does the rendering. You need to tell the GPU how many triangles you have. So this is technically the number of triangles. And then the animation just repeats. Any questions so far? Are we good? Okay.
Remember, WebGL built on GL.
OpenGL.
Yeah.
Yeah.
WebGL is built on GL that was in C, so a lot of the notation here are notations that goes to basic GL. Go L, GL triangles and so on. And many of these commands are just going. Many of these things are just constants that the GL talks to GL itself and says, oh, if this is 0.1, so if this is 1, I understand that the input will appear as triangles.
Yeah, and the 0 is again the offset of the triangles. If you want to skip some triangles, you can just put some offset. It's nothing fancy. Now, let's maybe quickly go over the shader program. So here you can see that this is the.
You want to flash what the output of the program?
Oh yeah, sure. So
not
this.
Everybody that is here was on Monday.
Yeah, so this is the output. So the output, you can see that it's kind of weird because it doesn't have depth test. It renders the earliest triangle that we loaded inside the GPU. It doesn't test for any depth. So they're just fighting which one goes on the monitor first. So if I go here and remember, we could enable these. If I enable depth test, and if I do this, select my texture, now they are not fighting. But again, the call face is still off. So our GPU actually renders the behind of the faces, just wasting a little bit. But yeah, you can turn it on and off, and I will show you later what is the use of that.
And for people that were here on Monday, roughly speaking, how many triangles do you see in this shape? Order of magnitude, 10, 20, hundreds. More than 20, less than 20.
100.
More than 20. Probably like 50.
Well, I showed you the last
I
time.
will rephrase the question, but I reminded before that there is a texture with an image with various colors and shapes that floats right here. Triangles here, all they did was said, I assign vertices of this triangle to this image that is a texture image, and now pixels of different colors will be mapped to different colors of the triangle. So, had you ignored all the color business that happens here, how many triangles do I need to generate? To generate a cube, I need 6 faces times 2. Each one is a triangle. That's for a cube. So for a cube, I need 12 triangles. Here I have at most 1, 2, 3 cubes. You got the answer. So 12 times 3 roughly would be a lower bound. And the complexity here comes from the texture. It's not comes because there is a lot of triangles. But understand, for a cube, I have 6 faces. Every face, I'll look at one of its diagonal. Now the face that is quad is split into 2 triangles. So from 6 faces, I got into 12 triangles. That's it. Am I right?
But that's not how it's divided up. Because the individual faces, like if there's 2 Fs on one face.
So let me show you how it works.
Beautiful point.
So here, each face is made out of 2 triangles, and you can even detect it by when it repeats the texture. You know that it's going to the next pair of triangles. So here we have this is like the number of triangles for each face. So we have 2 more triangles on this face, and so on.
But we talked about texture as a way to mimic the billboard. The billboard has one image, and we assign this image to the billboard, like 2 triangles. But texture in OpenGL is much stronger. I can, by assigning the coordinates correctly, here is the texture image. These pixels right here has cool name, textiles. And here is a big, say, roof. And I'm saying, take this image and use it to place, to cover the whole roof. And all I need to do is just to assign the correct size, and this image will cover the whole shape many times, like the multiple F that you see over here. So texture, one of the many applications of texture would be also that the texture image is much, much smaller than the triangle that you want to have it, and the same image should be wrapped once after the other many times, which of course asks for aliasing, which leads us naturally into map topic by itself. But it doesn't have to be one-to-one.
Yeah, so let me write down the texture coordinates. So this corner is like 0, 0, this corner is 1, 1. And again, like this corner is 0, 0, like this corner here is like 1, 1. So that's why you see that the texture kind of repeats. So each face has its own texture coordinates. Again, like 0, 0, 1, 1, and so on. So Now let's do like a glance on the shader program quickly. So here, if you remember from last session, the final variable that we need to set is GL position. Now here I multiply the projection matrix with the vertices, and this is just passing the coordinates, texture coordinates to the fragment shader. Now, for fragment shader, this is the final variable that you need to set, GL frag color, and I say go to the image. This is a function in OpenGL. This is the location of the image, and this is the interpolated texture coordinate. Now let's go to a more complicated example. So again, this example is not that complicated. So as you can see here, it's technically the same, but two things are different. First is that when we calculate the fragments, we can manipulate. We can say this fragment can be invisible. Now I made like a simple, like a quarter of a circle, something like this. I say just draw this part, and this part becomes this, like draw this part like a quarter, like a long quarter, right? Because this is 0, 0, 1, 1 in texture coordinate. And I say anything outside this circle, quarter of a circle, becomes invisible. So you can manipulate this inside your fragment shader. And so if you remember, let's go to the code.
Invisible become transparent.
Transparent, yeah, yeah. So the alpha
Not
becomes
invisible,
0.
Not invisible. Oh, okay.
Yeah, the alpha goes 0.
So it's not that it's only invisible, it's that you can see through it. Yeah.
Yes, let me show you how it works. That final variable GL frag color is RGBA. That's a fixed setup for like the OpenGL. So here I say go go calculate a distance. Again, I will give you this code. You can just read it and see how it works. And I just defined a variable that if it is inside like the boundary, set it to 1. If it is outside, set it to 0. So I forgot. So this is RGBA, but it is normalized, 0 to 1. It's not 0 to 255. So here I set the C variable that I say either 0 or 1 for the alpha channel. So here I get the actual, you see VEC3 here, it gets the RGB from the image and then adds the alpha channel to the end. So now the funny thing here is that I even used the global variable for the hardware. I just reused it instead of defining like a local variable. Now another change here is that I added light. So I have light direction here as a uniform. I do a dot product here, and I add the intensity of the light to the RGB value to all of them. So
is the model of which shading? Help?
diffuse.
Diffuse.
Yeah. So you can see that by this simple code, I can control which pixels to be transparent, how light should be handled. Let me also enable the depth test because I think it didn't have the depth test. Oops, where was that? It was a little bit ugly.
Went on the radar. Here is my light. Here is my light source. Here is my triangle, and the direction from the light to each point of the triangle is of course different, which implies that the cursor is different. Unless we really want to, we don't need to count at which angle the light arrives. Make sense? That was in a shader programming, there is, for every time that you are calling the fragment programming, one of your variables would be vector to the light, which might be very much different for different points on the triangle. Not something that you need to assign value to.
Yes, so here you can see that call face is disabled, so you can see behind the actual faces. But again, because it's transparent, it's good to see that there is something on the other side, right? So, okay.
Go in your pace, that leave a few minutes to show how to debug.
Sure. I will go to the last slide and a little bit about what can go wrong in your codes. So, okay, I mean, I can just show you this one just for the sake of it. Here, and I enabled call face, so now you cannot see behind the faces. So, okay, for this example, you see that we just changed the shader program a little bit. We just added the light, a uniform, and that's it. Any questions so far? It's the same example. Yeah, you have?
Yeah. Even when you had back faces on, it still looked like some of the
I was gonna say the same thing.
transparency was occluding some of the other quads.
Some of the faces were cold on the last one.
Yeah, I think it was because they were being blocked by the geometry still, or maybe it's a draw.
So let's think about it. Like,
You go back to the last
Yeah,
one.
can you go back to the version where
Uh-huh,
back faces were gone?
okay. So.
No, the enable in the code.
Oh, you mean the call
Yeah.
face? Yeah. Yeah, so if you pay attention, you can see behind the
But
faces.
you also can see where it's blocked. Like, look at that.
Do you
one.
see the F?
See how it's
Which part can you show me?
Right here. The back of this face shows up. It's gone. Shows up.
No.
It's gone right here.
Yeah, you're right. I know what's happening.
I don't know why
That's a
it's
good
being
call.
cold.
Is it just because of like the like are we getting are the fragments not like being added together?
I have another guess. My guess is the function for blend.
Yeah.
So for function for blend, I think I used two extremes. So alpha 1 and 0.
Yeah.
I think it does something like that because you can change your blend function, but that's my guess. I don't know what's happening.
Like a mask mode versus a true transparent mode, or
I can't remember the functions, but I don't even know for this version of WebGL if you can define a custom function. But again, that's my guess. I'm not sure why it's happening.
It was not the backface queuing.
Yeah, it should not remove back of that special kind of face, but it does.
is it depth maybe?
Depth buffer?
But why would it only have the one?
It is enabled. No, it's not. I think it's not. I think it's just the alpha function.
Do you have backface queuing on or off?
Now it's off, so it should show all of them, and depth
Well,
buffer.
it doesn't cull in one orientation of the app, but it does.
Like it seems like it's based on the order.
It's like it seems like it's orientation based whether it culls or not.
Yeah, I don't know. So the point.
Like even that top one, I feel like you should be able to see.
Yeah, top one. I think it maybe goes out. No. Okay.
Here is it's like
Yeah.
it does call it the top one.
Yeah, you're right.
And you can only see inside that little.
Oh,
That's
maybe
it.
maybe that some of those maybe that billboard on the side is not transparent fully, and such that it's blocking. You see what I mean?
Well, but if you look at the bottom of it, you can still see like on the like there's still the same issue.
Does it have?
Yeah,
Oh, maybe
yeah.
does it have something to do with the shading applied to it? Perhaps.
I don't know.
I
I
think
really
the two
don't.
vertical ones aren't see-through.
I really don't know. I can check and see
I think
what's
it's the two
happening.
vertical ones that
Uh-huh.
explain what way.
But there's not just
Look at this.
it's not just on the vertical one.
Yeah, it's
Okay,
not.
Yeah.
It's other places too.
Look on the bottom.
Look on the very bottom.
Yeah, the bottom
Right
also.
there, look at that. See?
Yeah, because it's this thing is blocking this right here.
Yeah, it's not like it's fully transparent.
See, this
It's
is
like
not
those
fully
ones being
transparent, and it's
right.
blocking this when it turns this way.
It's
This
not
starts
one
Oh,
blocking
there's
this.
also another thing.
Yeah, it's only
This
one side of it.
It's
Yeah.
from like
This one
side,
kind
right?
of shows up and then disappears. I think the far plane is too close. So it clips, so it's hard to see. Just right now, you see, just around here. It shows a little bit and disappears. I think the far plane is really close. That's why it clips out.
And I'll remind you that in the ray tracing, we didn't care very much about that there is a maximum depth and there is a minimum depth. Here we have to, and you will have these parameters, and once you set them, just things don't work. For example, you don't see things that are closer to you than the minimum depth or further away than the maximum depth.
Yeah, it has imperfections. I guess maybe the data has problem, maybe because it's hard-coded. Many things can go wrong. That's the difficulty of game development. That's why people make game engines, right? It's hard to make it. It's hard to debug. It's hard to make it, and you see a lot of lines of code. You don't want to repeat all of that for every single object, right? You need a game engine.
That would be unreal.
What a good job.
Yeah.
I'm happy because it was the most active and lively discussion that I've seen in this class for a while. So keep on doing it.
Okay, now if you don't mind, I go to the next example. So for the next example, we have two programs. One program does the background, another program does the actual letter. So I activate another program with another shader code that it's like the 2D background, and then I reactivate the letter and do the entire thing. Let's go over the code and see how it works. It's the complex example. So for this example, you see everything here is the same. Oops. Yeah, this is the old shader code. So here everything is the same, and then after some point I create another shader code. So I name it program background, and it does the background calculation. Not much different. So I add time, so that circle you see kind of grows and stuff. It's just time that just I send it as a single float number, a uniform. And now everything is the same here, same jargon, nothing important. Again, hard-coded positions and hard-coded texture coordinates. Now inside the drawing scene, if I remember, here we have use program, right? I say first activate the background program and send all these information, attributes, how it is made, it's 2D, all the stuff. I can even enable and disable. We are in the rendering loop, right? And then I say draw arrays, finish the background, just draw it, and then enable the second program, that is the letter, the 3D letter, and everything is exactly the same. And at the end, I say just draw and repeat the loop. So not much different, just another program that inside a rendering loop, I can have multiple programs that do multiple things, and I can just do my drawing. Any questions for this part? I think it's not. Yeah? Question?
I was just gonna ask, like, is it? No, never mind.
Yeah. So if you forget to enable a program, you will get a warning. That's part of the debugging. That's a good thing. That if you want to access a location, but it's not inside your program that you compile and you activate it, you get a warning when you debug. So that's a good thing. Now, okay, if you don't have questions, let's go to the last one. That is the one that was supposed to be your homework, render to texture. I mean, for mirror, you need to do that, right? It's like you have a fake camera inside the mirror that does rendering and then creates an image and put it on a billboard inside each rendering loop. So
So this sentence wasn't clear. So originally we thought that in this homework you'll have the mirror and it will wait for you for probably the next mirror. So using the mirror, you are basically having two passes you're seeing. One from what the mirror should have seen, making an image out of it and using this image as something to stick on the wall of the billboard when you are passing through all the objects again. We'll talk a bit more about the algorithmic part of it. No, we wouldn't go further, but for this homework it is not required. But it's still in the example that Amir will show.
Yeah, so what is happening here is also in the game development kind of literature. They call it baking. Baking was used in many old games. It's like a static lights. You do use fancy software to render the entire area, and then inside your game that is real time, you just put an image that has a static shadows. So you don't need to calculate those static shadows again. So, but theoretically it's called render to texture. So what I'm doing here is that I'm rendering the background and I create an image. Instead of that F letter image, I just put what I rendered myself as a texture. So there are a few commands that you need to use. I just show them quickly, especially because you don't need to use it for this.
Do you have a more complicated example with mirror?
No. This is the most. I have the video. If you want, I can show the demo for the old homework 3. So.
We take less than 30 seconds. It was saying
Sure.
what happens and what the process.
Yeah, I just.
Okay.
Yeah, I just show you here that inside the rendering loop, you can attach and detach. If I find it, yeah, you can attach and detach the frame buffer. So by default, your frame buffer is attached to your canvas, but you can attach it to a new buffer, a texture buffer, and attach like the output frame buffer into your texture. Now your texture is your image that you created, and then use that image inside the next program. So you detach the frame buffer from your canvas to a texture buffer that you created, and then you reattach the frame buffer back to the canvas. So that's how render to texture is happening. So again, inside a single rendering loop, you just attach and detach, and that's it. So Ellen, should I go over some common mistakes that can happen?
Absolutely.
Sure. Okay, it's not that long. I know I took almost the entire session. So now let's talk about potential issues. So the first issue is that let's not complicate things. Let's always use floats, no integer. So whenever you want to use a single number inside your fragment code, just be careful to put a .0, so to tell the shader that it's a float. It's kind of annoying because the error is just like failed to compile, and it's really hard to understand what is going on. Now, the next one that is, I think, the most sneaky one is that if you forget to send data to your uniform, by default it's 0. So let's say you send the light position, you were supposed to send the light position, but you forgot to send it to the GPU. And
everybody remembers what's uniform? The program at the top, server, decide about various parameters, tells everybody underneath it, here is the data that you need to use right now. And if in the next frame I want to change it, the server, the master wants to change it to be, say, the user or the camera location mode, change the uniform, and all the processors, all the shader underneath it, reads it. And the hierarchy is clear. The programs below cannot change the uniform. They can read it, but they cannot write into it.
yes, and especially because it comes from the CPU, from CPU to the GPU. But the danger here is that you won't get any warnings, you won't get any errors.
because by default all uniforms are 0. So you see that your scene is weird, there's no error, what's going on? You forgot to send the data to the uniform. So that's the most sneaky one. Next one, if you forget, let's say you were supposed to send 3D data, but you sent 2D. So the point is that, I think I said on the opposite side. So, I mean, let's say the triangles that you send to your attribute, it's not matching, all of them are not matching. You send positions for 30 triangles, but you forget to send 30 texture coordinates. You will get a warning, so it will run, but some of your triangles will be invisible. So that's a good one because it says, it even says how many triangles you were supposed to send and how many you're missing, how many you're actually sending. So that's not a bad one. Yeah, so.
You want to show on your program?
Yeah, sure. I mean, yeah, let's try. Let me just go here. The simplest example, go here. Let's do something like, yeah. I think if I do vec4 here, I hope I don't mess it up. If I say just 1, let's see what will happen. That's your example, right? Yes. Oops. And here. If I go here, yeah. So, well, Oh, okay, I'm sorry. Okay, I see. It was already RGBA. So let's do something really stupid. Nothing even related to the actual output. Let's say, float A is equal to 1. I don't have typos, right? Yeah, doesn't seem like it. Yeah, cannot cast const into float, whatever. So you have this error. If I just set it to 0.0, everything would be good. Sorry if it's very trivial, but yeah, everything now is good. Now let's go to the second example and forget to send the light. Second example, where do we send the light? Uniform light direction. Let's do that. Let's go here, open, and here. Everything is black. And if I go here, there shouldn't be any error unless browsers got fancier. There's no error. So if you forget uniform, that's the most bad type of mistake. Now, let's here, let me think. Let's go and just delete some of these. I delete some of the texture coordinates. Goodbye. Now we should get some warnings. If I do this, yeah. I was supposed to send 96 like data points, like floats, but I supplied 84 for attribute. So you get a warning. Oh, it doesn't show anything. I didn't know that. I thought that it would show something. But yeah, it seems like it doesn't show anything. Yeah, did I cover? Yeah, I cover all of them. Yeah, I think this is all you need to know.
Debugging is hard in the sense that to add breakpoints in the vertex program and ask what is the value of a variable. That's hard, impossible to run in your GPU and you don't have nice debugger.
especially on browser. If it is outside, there are some limited tools, but yeah, usually that's why it's hard to make game engines and it takes a lot of time to release one. So, any questions? Now you're all set to make a fancy game engine. You can literally make the fanciest game engine Unreal by shader programming. What the fanciest developers in Unreal do is that they optimize shader programming and all this stuff. So they don't do any hacking or something like that. So if you are getting really good, you can make fancy stuff. Am I dismissed?
Very useful sources. I can easily number 15 minutes.
If you want, I can show them Shader Toy. There is like a website that you can see. Yeah.
Of course. What you're finding is one big warning. It's extremely powerful, and OpenGL is a more powerful tool, so it's very tempting to ask what this parameter is doing. It's a huge mistake. It's a huge time thing. Leave most things as is because it's default that allows you to do fancy effects. That unless you want to do them, just don't. You need to get to the maturity of there will be plenty of lines in your code that you are not sure what exactly happening inside them or parameters there. And that from resources that I looked at, it's hard to, I'm not trying to give any grades to Amir or Min, but it's hard to teach JavaScript well, WebGL well, from my point, or at least I didn't see any great resource because there is no clear linear order of which to teach it. There's too many things that depends on other things. And whatever you start to teach with is the wrong thing. So that's why. So yeah, you will have to do check your packet about what does this thing do exactly, or look at other resources. We can give you the starting point, but as we said, there is no clearly now order that we are saying, here are all the things that you need to know.
You can even make music by shader programming. I can't remember which one has music, maybe this one, but you can like define different, how to enable it. You can define different types of like sound, like saw, a square, all this stuff, and you can make fancy even musics. Some of them are really interesting. If I find one of them, something like that, I can't remember its name.
Needless to say, this animation at this time with ray tracing in single CPU.
Yeah, it's a little bit heavy. You see that my computer has a little bit of hiccup, especially because this doesn't have a dedicated GPU. So maybe I need to close some of them so it can load. Or okay, yeah. Morning. If it shows up.
I didn't try to criticize your laptop.
Yeah. Yeah.
I'm trying to justify that the pain of going to the WebGL is hopefully justified by seeing how dramatic the performances are. The thing that with a single CPU, well, we didn't let them do the mirrors that involved multiple depths, but already it runs probably in the orders of minutes, even without in your images, if you wanted high enough resolution, even for static image. So it's many orders faster, even if you don't have GPU on your computer.
So the beauty of Shader Toy is that in this scene, there is no vertex. All of them is done by math. You can make 3D objects by just math. Just saying that if I shoot like a ray, let me go over.
You have the waves over there.
Let me. There's also a live one that someone on YouTube showed how to do this. So, yeah, if I find it. Yeah, this is a famous one. So again, even this one that you see, it's by math. It has texture as file, but it is done by math. There is no like 3D model involved here. There are many examples on Shader Toy, and some of them are really heavy. Oh yeah, sure. Sure. Let me. Yeah.
Very fancy about 8, 8, 8, 8, 8, 8. Doing one of the homeworks, maybe last homeworks, where you see the reflection plus reflection, where every pixel by itself knows the normal at its very moment, the direction to the light, and all the remember the specular effects towards the viewers that are all changing, and all happens well in real time, based on, once again, every pixel know what is its normal, refraction, Snell law happens, and that's why you got specular spots when the, remember, direction to the normal, direction to the light behaves like a perfect mirror.
Yeah.
And
there are examples on like creating geometry on the fly by math.
so
That's the manual route set, like it just like repeats like fractals.
oh,
This is the actual source code. That's it. Like with this math, you can do that.
it's a factor.
Seems like it.
I think it's
Yeah.
okay.
A lot of them are based on manual broad sets, and then they'll distort them around them.
Yeah, I can't remember how to find.
Is that an epilepsy warning?
Yeah, so again, it's hard to debug, and I can't even. It was hard for me to believe that this piece of code makes this. So I decided to change, I don't know, like this, and recompile. Let's see if it changes. I mean, many of them are just really hard to believe. I try to learn, but yeah.
So you see the semi-transparency here, and how a few layers of transparency, what the A buffer, stencil buffer, as we play with this, both because we want to speak about things even like green screen, blue screen, some patients of colors, but also because the very recent technique of Gaussian splatters, but Gaussian.
It's splatting.
Hmm?
Gaussian splatting.
Gaussian splatting. Gaussian splatting that just create the 3D model by assuming relative, assuming partial non-zero transparency of Gaussian, and just let the A buffer accumulate them, which is what it's made to do in hardware, so it's done very fast.
Yeah, so just to give you another hint, inside the where was that? The complex example inside the shader code, I used a variable that is used in shader programming.
And you also
That's this
one.
one.
Second to show the video with mirror.
Oh yeah, sure. So this GLFrac core, it can tell you what is the pixel value inside your scene. So you can really access the actual XY of the pixel value. So that's also very useful in shader toy to do all this stuff. And let me leave.
You want to see maybe because besides the mirror, we need to do.
Yeah. So here you can see a render to texture that renders by the fake camera first and then put as an image on the billboard. So here you can see one debugging technique. It's best to use like a weird color for your clear color to see if really the billboard is that showing or is there a bug in my code. So you see I use all these colors just to debug and making sure that my stuff are just shown properly. Any questions?
And so that would be a simple example of your triangulated mesh. You are building the object file, like we said. You see the specular and diffuse shading that appears on the faces there, which, to remind you, we talked about it Monday. You need to compute the approximated normals at the vertices and then use the approximations, the interpolation that the shader fragments programming gives you to approximate the normals of each individual point and multiply by the light. Very simple. Once you remember how to do it and how to go from the normal to each vertex, and you can ask the vertex shader to compute the actual normal. But what you actually need to do to create the normal, which is like in between two vertices, is to take the real normal here, the real normal here, and then assign to both of them what I think is a normal, because it does because OpenGL doesn't impose itself. It says, okay, if you want to tell me that that you OpenGL will be completely cool with you saying, if you want to tell me, to ask me, what is a normal, here is a triangle, if you want to ask me what is a normal at this point, I can compute it for you, or you compute it by yourself. You know, that's a representation. But what you need to get the ground and from interpolation is to say, hey, vertex shader, I'll tell you that this is the location of the vertex, but the normal that I think about it is actually this guy over here, which is not the real normal, nor the real normal here. And for this vertex, I'll say this is the real normal for this vertex. It's an attribute of the vertices, and then numerically every vertex, every fragment will have its own location of the normal, which is computed based on its vicinity to each one of these fake normals that you assign. So that's how you created the smoothness of this factor. It's not flat shading change over here. The part of the mirror that you do in the next homework is that you see that the back sides of both these guys. How are we doing the back sides? And I'll let you go on in, give me 30 seconds. If this is a room, I'm looking at the room from the top. Here is red, red, green over here, and here is a viewer. Look to the back, but on the back of this room there is a mirror. So I need to see. Let's look a bit further. I need to see, like placement on 3D, the red point. The eye should see the red point. Why? Because the eye sees the mirror and the red point appears in the mirror. So how do I do it? By using all the power of the depth buffer. I will think about this mirror. I will think about the eye. Now I'll put the eye over here, call it I prime, it's in your theoretical part to think about what are the new parameter of I prime, what's the angle, what's the angle of view, how far away it is, and I'll take an image of everything in the room, including this red point, including the depth, from the I part. And now I have in my color buffer an image that looks just like, let's take all of these as an image that we can reattach, use it as a texture now, and this surface stopped being a mirror, it just starts being a normal billboard with an image put on it. It doesn't matter at all that this image on the mirror is on the billboard is not an image that it read from a PKM file. Instead, it's an image that it's prepared for itself one iteration ago. And it just read it as a texture. And now I'm doing another pass of the Z buffer when the eye is here, including seeing this poster, the billboard, which is a mirror, at which you see the reflection of the red point. And waving, it also appears in Homer 3.
You haven't posted the repository as the due date.
We are replacing it today, and the due date is as usual. Wishful thinking due date.
Okay, so it's not going to be due.
I'll put it like a couple of days after the end of the vacation, and people will say, come on, I was doing other things. But yeah, so aim for 2, 3, 4 days after the end of the vacation, we'll effectively good place to premiere and debug, but reasonably soon after the vacation, it will be. Okay?
Almost a year ago.
It says due.
2024.
Yeah, 2024, so it's a little bit late. I'm getting hurt.
What are you going to debug this time?
There were extra variables in my Vertex file that were screwing up how things were being transferred to how long. It's all working now. I can show you what it looks like. That's a picture. I mean, it was just, I texted it to most of us.
Yeah, they're nice actually. Your death level look exactly like the one on your slides the other day.
Maybe they did. I don't know.
Yeah, so it's
Doing something like fucking.
the normal mapping. So now I'm
So I was
moving.
emailing you about tuning in the presenter too. Okay, the theory profile that you had, and you
Yeah,
said.
well, it should be fun. They're just cute faces of the kids.
This one was up there, that's when you put it in.
Oh,
Normal
So I was
time
doing
and
this
location.
It doesn't matter.
yeah, so you submit on the wrong person, right?
I didn't submit it in here, but
Also,
I need
yeah,
to submit it.
Okay, just email me, because I need to have that, like,
having some meeting halfway.
just remember when I grade, if there's any bonus or credit,
and start
bonus stuff.
calculating.
Okay, so I just emailed you, you'll put it in here, I guess, or.
No need to change it, just email me that you sent
Oh, well,
it, you
it's
submitted
that
on
case,
grad
you
instead
get
of undergrad.
differential.
Okay, so I just submit it here.
Yeah, just email me so that I can remember.
Okay,
cool.
The show the basic dual
No.
is just taking the average of the three.
No, I mean, right now, you can see it's super basic, like there's nothing really saying. This is, it was just two.
My question is, the dual slash form are
Yeah.
more complicated than this, but less complicated than what you're telling me. It says I'll smooth it by assigning to the corners the fake normal instead of the real one, and interpolate between the fake normals.
Yeah.
So that's normal.
But that would be correct for a flat cube face. Cause I just want the normal of the face.
I was under the impression that that's what you wanted. If you don't
No, I
follow
just
it,
didn't understand what it was doing. I was like, well, but here it doesn't matter because the normal is the same in each
Okay,
vertex.
so I combine it with the question that you asked.
Yes, you were answering the correct question, but I didn't know what I was talking about.
Good, and understand,
This is-
you get to the point that
Yeah.
you want to tell the class what it is, you know, break and break.
Hopefully over break, in addition to this
I
moment.
don't think that we have many students, well, sorry. I interrupted. Well, hopefully over the break.
Hopefully over the break, I'll be able to calculate all of this scattering geometry that I need, and be able to like render make like simple renderings with, the geometry.
If you think that it's interesting to the class to hear about it, or not less interesting than hearing it. And it's cool research project by all means.
Yeah, well,
and
I'm
you
hoping
your way.
I applied to present at a conference in August, so hopefully I'll have I'll have a working version by the end of the semester for this poster that I need to make.
Unless there is royalty stuff that you are.
No, it's all in the set.
Yeah,
No,
and this also okay with you put the code in half a year, and in the meantime you can give us in some vague research to provide it.
No, I can give a description of what it's doing. I mean, we're basically using the Flynn Fong, specular shaping model, but then we're looking at the polarization at the same time, just using like Fresnel coefficients. Do you know what? Are you familiar with Fresnel coefficients?
Yes.
So we have like the S&P coefficient. So right now what I'm working on is you have an incoming ray and an outgoing ray, and calculating the geometry of that. And then we just have instead of the BREF being scalar, it's a 4x4 matrix with the S&P.
I communicate for the template.
Yes. You need what?
No, I'm good.
Okay.
Have a good day.
Okay.
But yeah, hopefully by the end of the semester I can put together a presentation that shows it actually rendering the scene.
Not wasting out. If you're proud, it will be part of your grade and it will be interesting for if you don't want, no question. No. If you have stuff to talk about,
It's not related to this. Sadly. I wish.
so besides the snake, what else do you have?
Oh, animal wise?
Yeah.
Oh, so many things.